So what are some challenges in drive cycles? And really these challenges related to dynamic power measurement. Well, for the certified range test, one of the challenges is having transparency to equations. We really want to know what the measurement period is and how energy is calculated so that we can not only get a number, but understand where the number came from and have confidence that it's correct. We want to be able to know exactly the period we're using, how the energy is calculated, when we're resetting the energy calculation, when the energy calculation starts, because it's cumulative. We really want to know how these are being executed. We don't want a black box. That's one challenge, is understanding the equations and not only how they're executed, but when they're executed, because energy is cumulative. If you have energy accumulating before the test starts, that could be a real problem. We're going to have limited access to measurement points. We make vehicles so that they don't fall apart and so that me and you can't just go and grab high voltage cables. So physically getting to some of the measurement points can be a challenge. And I won't belabor this, but getting sensors and getting measurement in can be really difficult if there's short runs or difficult places to place sensors. A lot of these tests require feedback to the dyno. Many times the certified instrument by the governing body is the dynamometer, and you want to have a real-time feedback from any instrumentation to the dynamometer so that it can be the certified instrument and you can monitor the test in real time. You want that feedback. We mentioned that these tests are running from full battery to empty. These vehicles have significantly increased ranges. These tests could take 10 or more hours. You don't want to have to rerun a 10-hour test. You want that feedback so you can know if something's going wrong immediately. You need to operate in a wide temperature range. You have to worry about electrical noise because we have these high frequency inverters. We really do have to be concerned with, is my cabling correct? Is my instrumentation isolated? All of these things to make sure we're not worrying about electrical noise. Because there's a lot of inverters, there's a lot of EMC, EMI. Lastly, accuracy. Accuracy is really important because if we have a vehicle that has a 500-mile measured range, but we have an uncertainty of 50 miles, we can only certify that vehicle for 450 miles. We can lower that uncertainty. We can raise that effective range. So accuracy is also important. So these are considerations for the certified test. Now, if we remember back, challenges in the engineering test are going to be the same as the range test, just more of them. Again, limited access to voltages and currents. We're only going to be able to get at certain measurement points. We might have to hack some things together, change some cables, but we're going to have limited access to those voltages and currents. Again, if we remember, we have 10 to 20 measurements with many configurations and many different ways to look at it. And what I have on the right-hand side here is a screenshot from our software, which tries to simplify this configuration, where we have 2 batteries, we have 2 inverters, we have 2 motors, and we have 4 wheels. And we try to break it out so you can understand the power usage of each component. And this is really inspired by these many measurements and many configurations. Because if you have 10 different power using sources, you can view the voltage, current, power of each individual component and have a unique name with it so you can understand what your system is doing, even for these complex configurations with many measurements. There's no steady state frequency. This comes back to that dynamic power. The speed and torque is constantly changing. We really want to understand, what is the measurement period for DC power? Again, if we're coming back to make decisions on changing components or updating controls, we want to make sure we understand where these measurements are coming from to make decisions. So we want to know the period for DC measurement. We also want to know how the integration is performed. Because again, if we're making these decisions, we want to have very correct information. We want to know exactly how it's being performed, and that also helps us correlate back to models if we're doing a vehicle level model. These vehicles are constantly changing states. We have transients, we have clutches, we have multiple machines phasing in and out. Again, right in line with this no steady state frequency, right in line with those drive cycles and understanding that dynamic power, we want to be able to pick up these transients, clutches, and multiple machines. We want to have that data recorded for each of these measurements for that entire test period, that 10+ hour test, so that we can understand each interaction. We can see the energy flow between these, even as things are phasing in and out. Because that dynamic power, catching those dynamic scenarios, is really important. And we might want that down to the millisecond or less range. We might want that really fast update rate. Again, this is something that HPK can help with. And then lastly, torque is difficult to measure. If we really want to kind of understand the components, we might have to take wheel torque and then get that back to some sort of calculated value. So torque is difficult to get to, mainly because placing a sensor in the vehicle is challenging. But from the electrical end, because we want to understand power flow, we want to be able to take many measurements in one location. We want to be able to visualize them. We want to know how power is calculated. And we want to be able to trust our dynamic power measurements. So there's definite challenges because there are a lot of measurements and it does execute for a long period of time. Component level drive cycle test. Because now we're measuring AC, this no steady state frequency becomes even more important. Vehicle speed's constantly changing and we want to trust that value in the dynamic periods. We want to look at these constantly changing states and understand them. We want to measure dynamic torque and speed. We want to know what our torque looks like in a transition if we clutch in a motor, because we don't want to overshoot and we don't want to get there too slow. It's a really challenging thing, dynamic torque and speed. And then a lot of times we'll want to relate these signals back to the CAN bus. And I haven't talked about CAN bus yet, but the vehicle is speaking to CAN. Each component is speaking to the vehicle controller over CAN. And the vehicle itself is estimating what its parameters are. It's estimating its power output, it's estimating its torque, and it's publishing this on a CAN bus. And at the component level, we want to make sure that what the vehicle is thinking matches reality. So we can measure the CAN, we can measure the real signals, and we can compare reality to vehicle. And we want to make sure these match. So there's additional challenges of dynamics, of constantly changing states, of dynamic torque and speed, and then of correlation to other values. So the component level test is difficult as well. And if we can correctly characterize the component and we can correctly characterize its CAN bus, we can then bring that back to the vehicle level test and improve that range. Cool. So we've looked at challenges in the 3 different types of testing, and a lot of it comes down to understanding our measurement period, having a high rate of data, and having many measurements in one place.